So very good afternoon, everyone. Before we get started, we request all the participants to kindly mute your microphones during the presentation, and please, towards the end of the program, you may unmute yourself and ask the questions. Also, we request you to please switch off your cameras. It's better that only the speaker is switching on his camera, because that will look good in our recording. So with that, we'll start our presentation. So very good afternoon, fellow foundrymen. It gives me immense pleasure in interacting with you all for the 37th program, which is being conducted by the Institute of Indian Foundrymen Chennai chapter. This is an online webinar, and this program is jointly conducted by the Institute of Indian Foundrymen Chennai chapter and the IIF Andhra chapter. To get things started, we now request Mr. R.A. Prasad, Chairman, IIF Andhra chapter, to welcome the gathering, please.
Good afternoon to all foundrymen.
Good afternoon, sir.
Are you able to hear?
Yes, sir. Yes, sir.
First of all, let me thank Chennai chapter for organizing the program in association with Andhra chapter. Mr. Saktivel and Mr. Vignesh, thank you, both of you, for the program. I have the privilege of welcoming all the foundrymen today for today's talk on riser design for ductile iron castings by Mr. SP Arunachalam, Director Technical, Shri Venkatachalapathy Alloys Pvt Ltd. And welcome all the foundrymen for today's topic, which is actually the more widely used castings nowadays in all sectors. And it should be useful and fruitful to all the foundrymen for today. And thank you once again for the Chennai chapter for the same organizing, and welcome all the foundrymen for today's lecture. Thank you.
Thank you, Prasad, sir. To now introduce our speaker for the day, I now request Mr. K. Hema Prasad, Council Member, IIF Chennai chapter, to introduce the chief guest, to the speaker to the gathering, please.
Thank you, Mr. Vignesh. It's my pleasure to introduce today's speaker, Mr. SP Arunachalam. He completed his BTech at University of Mysore in 1971. Further, he completed his MBA at Tyagaraja College School of Management in 1996. He worked and gained a hands-on experience in reputed foundries such as Tamil Nadu Alloys Foundries Limited, Hosur, then Binni Engineering Limited, Meenambakam. He also worked as a general manager at Subhadra Alloys Pvt Ltd, Trichy, Aruna Alloy Steels Pvt Ltd, Madurai, and Pioneer Alloy Castings Limited, Gumudipundi. Presently, he worked as a director technical with Sri Venkatachalapathy Alloys Pvt Ltd. He has a vast first-hand experience in patent development, methoding, production processes, and quality management systems of gray iron, ductile iron, and steel casting manufacture. Totally, he has a 50 years of vast experience. Now the floor is yours, sir. Thank you.
Thank you, Mr. Prasad. Thank you, Mr. Ramanan, Vignesh Ramanan. Good afternoon to everyone who have logged in to attend this webinar. At the outset, I would like to thank the organizers of the webinar, that is IIF Chennai Chapter Chairman, Mr. Saktivel, the Honorary Secretary, Mr. Vignesh, along with Andhra Chapter Chairman, Mr. R.A. Prasad, and Honorary Secretary, Mr. V.M. Krishna Kumar, for giving me this opportunity to present my technical paper. The topic of today's presentation is riser design for ductile iron castings. Next slide is okay. The quality demands of castings have increased in recent years and to produce high-grade castings economically. The importance of methoding cannot be ignored while the foundry unit tries to compete in the open market nationally and internationally in the attempt to produce castings of the highest quality to be used in the industry. These days, in such a fiercely competitive world, and every foundry doing that extra bit to have an edge over the next, one must strive at all times to be abreast of the latest developments and also aim to achieve the highest quality castings so that the product does not come back to bite you later on. One bad product is enough in this competitive world to knock us off our feet. One bad product could even cause such a flurry that all the castings we sent back. One bad product could even cause such a flurry that all the castings be sent back for want of rechecking and for want of corrections after a series of tests conducted. Such a series of activities not only cause the production and testing to fall back a step, but also cause the rest of the clients eyeing the company suspiciously. Be one step ahead. Quality castings, first time, every time. Customer complaints must be unheard of. Look for Six Sigma or higher standards of quality. Think for the best in the industry. Aim and achieve that. The following processes form part of casting production: pattern design, methoding, equipment maintenance, molding, core making, mold assembly, melting, coring and finishing, sand control, metallurgy, operator training. Pattern design is very important. It is the beginning process for a casting production. The drawing has to be studied carefully. The parting lines has to be established. Core prints, core boxes, they have to be designed. In order to do that, you have to first keep in your mind the proposed gating system and the riser. All these things to be considered before pattern design. Next comes methoding. Equipment maintenance is also very important. Equipment maintenance in the sense pattern maintenance, core box maintenance, match plates, molding machines, molding boxes, and all related materials. If they are to be maintained and kept in proper condition to have the castings without any defect. Then comes production side, the process of molding, core making, mold assembly, melting, pouring, and finishing. Sand control, metallurgy. The operators are to be trained. They should be trained, and their training should be upgraded based upon the latest developments and on new equipments and new processes introduced in the particular foundry. Out of the seven items mentioned previously, serial numbers 3 to 7 are common to all products produced in a particular foundry. Once these processes are established, they do not vary from product to product. But pattern design and methoding are unique. They vary for every item. Methoding consists of the following: gating system and risers. Gating system consists of downscrew, running system, ingates, and vents. Risers provide feed metal to the casting during solidification. To produce individual castings or small runs before mass production are uneconomical. Methods were therefore developed for analyzing in a simple manner the physical process occurring during the solidification of castings, and then applying the appropriate practical measures. These methods stem from Shorino, who was the first to answer the basic question, how long does it take for a casting to solidify? This method enables the feeding conditions in the casting to be determined with more certainty. This in turn results in less rejections, a more punctual timetable, and economies in liquid metal. Modulus, the term modulus means volume divided by surface area. It is expressed in linear measurement units such as centimeter, millimeter, or inches. Many people fight shy of calculating volumes and areas and consider the computation of modulus to be time consuming. However, we shall show in this technical paper that modulus technique is simple in conception. Scrapped casting is very expensive. It is always cheaper to do some basic thinking beforehand rather than cast scrap either once or even several times in succession. Preparation takes time, but its importance cannot be underestimated in view of the danger of casting scrap. What is a riser or feeder head? A riser is a reservoir built into a metal casting mold to prevent cavities due to shrinkage. Most metals are less dense as a liquid than as a solid. So castings shrink upon cooling, which can leave a void at the last point to solidify. Risers prevent this by providing molten metal to the casting as it solidifies. The functions of a riser are to compensate the reduction in volume of a casting from superheat temperature to solidification temperature, compensate for decrease in volume, consequently increase in density during solidification, provide a pressure head for feeding the casting during solidification. For riser calculation, certain concept has to be first understood, then it will become easy to calculate the riser. One is modulus of a casting, second one is thermal gradient, third one feeding range, fourth one riser efficiency, fifth one riser neck. As already told, the term modulus means the ratio volume to cooling surface area and is expressed in millimeter, centimeter, inches. The concept of modulus. Solidification time of a casting depends upon the area of contact with the mold walls. Dissipation of heat from the molten metal in the mold cavity takes place through the mold walls. More the cooling surface, faster the production. For example, if 10 kg of molten iron is cast, first as a sphere and then as a thin plate, the plate will solidify much faster than the sphere because 10 kg is given off over a much larger surface area in the case of a plate. Larger the heat dissipating surface associated with a given volume, the faster the solidification. The concept of modulus was introduced by a Russian scientist, Mr. Shorino. Robert Lodover, a German engineer, split the castings into different simple sections and applied the modulus principle. This simplified the modulus calculation. The casting modulus can be increased by thermal padding by use of insulation or exothermic by use of or molding materials with chilling. Now here is a table showing the solidification modulus of some simple shapes. The first is a large plate. by more than 5 times the thickness, A greater than 5D. Assume an imaginary cube is removed from the large plate. The sides of the imaginary cube are 1 centimeter by 1 centimeter. Thickness is D. Volume of this imaginary plate is 1 centimeter square by D. Area is 2 times into 1 centimeter square. 2 times because there are 2 cooling surfaces. The other 4 sides are non-cooling surfaces. Modulus is equal to D by 2. Similarly, a long bar. Here also, assume an imaginary section of 1 centimeter length is removed. Volume of this imaginary section is A into B into 1 centimeter. Area is equal to 2 into A plus B into 1 centimeter. So, modulus is equal to AB by 2 into A plus B. The next case is a cube of sides A. There are 6 sides. Each side, area of each side is A squared. A is equal to 6A squared. Volume is equal to A cube. Modulus of this cube is equal to A by 6. The next one is the cylinder. Cylinder of radius R and height h. V is equal to pi r squared h. Area is equal to 2 pi r into r plus h. Modulus is equal to RH by 2 into r plus h. Next comes a sphere. Volume of the sphere is equal to pi d cube by 6. Area of the sphere is equal to pi d squared. M is equal to d by 6. This is very similar to the cube which we have seen earlier. If a sphere is inscribed inside this cube, the diameter of the cube sphere being A, then the same result will occur. Next is a bush. The bush, if the bush is cut along the hatched portion and straightened, then it becomes a long bar. That is, M is equal to AB by 2 plus 2 into A plus B. This is the bush. In the modulus of junctions, this is the case of a cover with some rib inside. At the junction of the cover and the rib, there is a fillet. Here, heat is accumulated in the fillet. The accumulation of heat in the fillet increases with rising casting temperature. In practice, it is sufficient to estimate this influence as follows. Draw the intersection on a scale of 1:1. Estimate the sand fillet effect based on the casting temperature. Draw the inscribed circle which determines the modulus. It is removed in this case. It is now removed. Here it is removed, and an inscribed circle is made. The circle is slightly larger than the junction area. It is allowing for the heat effect, temperature effect at the fillet. Simplification of modulus calculation. As angular bodies and round figures inscribed in them have the same modulus, they represent mutual simulation bodies and either can be used for computation of modulus. Irregular circular cross sections can be replaced approximately by rectangles. The technique of using simplified or equivalent shapes is a technique of great practical importance and enables numerous problems to be solved without the costly process of trial and error, such as, is a casting wall heavy enough to feed a heavier section without forming a shrinkage cavity? Is it necessary to place a feeder on a thicker section? As a whole range of casting and feeder calculation is based on determination of modulus, one should attempt to work out some modulus calculation by himself. As soon as a certain amount of practice has been obtained in carrying out the process of breaking down the casting into simple basic components and constructing equivalent bodies or sections, it will be found that the modulus calculation itself is very simple. Riser modulus. Consider a cylindrical open-topped feeder head. A continuous shrinkage cavity in the form of a hollow cone is formed. A hollow cone is a cone removed. The line of curvature is practically a parabola. The cavity is formed by evacuation of feeder by the casting, resulting in substantial reduction in volume of the feeder. This causes a reduction in the modulus of the riser than it originally was. The decrease in modulus of the riser during solidification experiments have proved this. Thermal gradient. Gradient is the change in temperature over excuse me, 1 minute. The stepped bar shown in figure above solidifies the thinnest portion first, days later. This is because of the amount of heat to be dissipated. Thus, a temperature gradient exists due to which the solidification progressively moves towards the riser. To obtain a temperature gradient, it is sometimes sufficient to that of the casting and the artist in the feeder. Here a plate is shown with a riser, cylindrical riser. The temperature gradient can be seen. It is at the tip, at the end zone, it is lower, goes on increasing. Then at the riser, it is suddenly very high because of the amount of heat in the riser. This is the temperature pattern stop pour through the feeder. In order for a cross section to
Sir, Arunachalam, sir.
liquid, tell me. Hello.
Sir, your presentation is not visible. You can stop the sharing. Again, try to share it, sir.
Okay.
Yes, sir. It is good, sir. You can go, sir.
Okay. In order for a cross section to remain liquid longer than a laboring zone, it must contain at more heat. A section with a longer solidifying time also has a larger modulus. Experiments have shown that the modulus must be higher by a factor of about 1.1 for sections to be able to feed the adjoining section. Feeder heads also form such metal supplying sections. The feeder head modulus must be at least 1.2 times larger than that of the casting modulus. The next is the feeding range. The length of the casting which can be fed satisfactorily is called the feeding range. Metals, while solidifying, they solidify as crystals. Here in this figure, the first phase of solidifying, a crystal is formed. The next phase, at the tip, some more crystals are formed, deposited on the tip. Further, it goes on similarly, just like a fir tree, sideways. In every tip, more and more crystals are formed and deposited. This is a dendrite. In many metals, dendritic crystals, fir tree-like structure, grow from outside inwards. Next is the three phases of solidification of a plate. A solid edge zone is formed with a broad liquid zone between advancing crystal fronts. Liquid metals flows freely and always remains in contact with dendrites, thus filling up the space. Secondly, the crystal peaks constrict the flow of metal and finally come into contact. Eventually, the flow of metal is cut off and sinkage cavities are formed. First is a plate having an end zone. Here the riser feeder is not shown. Next one, plate with end zone. The riser feeder head is shown. In the third one, a plate of shorter length feeder. Fourth one, plate. The first figure shows end section of a plate. Heat radiates from three sides with the formation of a solidification wedge. In the second one, feeder section of a plate. Here, this is a feeder head and this is the plate. Diminished growth rate of the dendrites nearer the feeder due to its heating effect. Hence, a solidification wedge is formed. In the third figure, it is a shorter plate with feeder head. End and feeder zones are continuous, giving sound plate. This is the end zone. This is having a wedge. Next one is nearer to the feeder. Feeding is sound. Next one is a longer plate. The end zone is further away from the riser. End and feeder zones are not continuous. Cavities are formed in the central zone with a parallel solidification front. The first one is end zone, is a parallel solidification zone, is a wedge formed zone near the riser. Next comes insulation and use of certain materials in the mold will delay the cooling of the molten metal in the mold. These materials are two types. One is insulating, the other is exothermic. Insulating materials have lower thermal conductivity compared to sand. They do not initiate any exothermic reaction. Exothermic materials initiate exothermic reaction when molten metal comes in contact with them. They are self-heating insulating materials. Insulation or exothermic feeder heads. Exothermic sleeves extend the solidification time of the feeder heads. A smaller size feeder head can be substituted in place of a sand feeder head. The ratio of the geometrical modulus of the sand riser to the geometrical modulus of the sleeve riser with equivalent solidification time is known as modulus extension factor. MEF is equal to geometrical modulus of sand riser divided by geometrical modulus of sleeve riser with same cooling time. The shape of the shrinkage cavity in the exothermic feeder exhibits a cylindrical shape. It increases the riser efficiency to as high as 35 to 50%. The value of MEF and feeding efficiency will be provided by the sleeve manufacturer. The benefits of insulating are exothermic sleeves. Exothermic sleeves, they increases the casting yield, reduce the energy cost per ton of wood casting produced, increase maximum casting weight achievable per batch of molten metal, saves cost of costly alloying elements. Having gone through the required concepts which are to be understood, now we come to the next stage of designing a riser. It has 5 steps. Steps for riser calculation. First, break down the casting into basic shapes and feeding areas. Number 2, determine the section modulus of each feeding area. Number 3, determine the volume of feed metal required for each feeding zone. Number 4, calculate and select the riser for each feeding zone. Number 5, calculate the dimensions and distance of the feeder necks. Now we come to an example of modulus calculation. This is a flange detached from a wall casting. The diameter of the flange is 360 dia, ID is 130, thickness 60. And there is in this one there is a corner effect. So we have to draw an inscribed circle to offset the effect of the corner. This here it is inscribed, it is slightly larger than the thickness, it is 72 millimeter. Due to the corner effect at the junction, flange thickness should be considered as the diameter of the inscribed circle shown. We can consider it as a bush which we have shown in the table. Models of the casting. The models of the bush which I have seen in the table is models of casting MC is equal to AB divided by 2 into A plus B minus T. T we are taking because here it is 50. This is a non-cooling surface. So this has to be, non-cooling surface has to be removed from the casting for calculating the casting modulus. Width is 115 mm, that is 11.5 centimeter. B is the thickness. Thickness is 60, we have to take it as 72. T is the non-cooling system, that is 50, that is 5 centimeter. MC, modulus of the casting, is equal to substituting all the values, we get 2.55 centimeter. Now riser calculation. For this MC of 2.55, the riser should be, modulus of riser should be 1.2 times of the modulus of the casting. MR is equal to 1.2 into MC, which is 3 centimeter. Since the riser modulus is very large, we can consider an exothermic riser. Otherwise, hand riser will be too large and it will be uneconomical. An exothermic riser can be considered. For exothermic riser, generally 1.6 to 1.7 is the MEF given by the manufacturers. Here, we are going to assume 1.7 as the MEF. Weight of casting is equal to, we are calculating the weight, area into thickness into density of the casting. Density of the casting considered as 0.0076 kg per centimeter cube. We are getting 40.34 kg. Weight of fed metal required is 40.34 into 4% of that, where we get 1.616 kg. Now let us consider the 80 mm dia and 200 mm height sleeve riser. Modulus of the riser is geometrical modulus of the riser into MEF. Riser diameter is 80 mm, radius is 40 mm, that is 4 centimeter, into height is 20 centimeter, divided by 4 plus 2 into 20 centimeter, 2h, into MEF 1.7, that is 3.1 centimeter. This is greater than the required MR of 3 centimeter. So we have, modulus wise, this is okay. Now we have to consider the feeding efficiency. Weight of molten metal in the riser is, it comes to 7 kg. At 35% efficiency, the feed metal available will be 7 into 0.35, 2.45 kg. Whereas we require only 1.616 kg. So this satisfies both the conditions. Diameter 80 mm into height 200 mm riser is the required sleeve riser. Now calculate the dimensions of the neck. Required riser neck size M and MC is equal to, Mn is equal to MC into 0.5. It can be from 0.5 to 0.7. We are taking this case as 0.5. If the length from the casting to the riser is too much, this factor 0.5 will be increased, maybe 0.7, 0.8 like that. Now Mn is equal to 1.25 centimeter. Let us consider a cross section of 50 mm by 50 mm square. Modulus of neck is equal to 5 into 5 divided by 4 into 5, that is 1.25 centimeter. So we can adopt this particular diameter of the riser and the neck as 5.5, 50 by 50 square section. Next, we have to check the feeding distance. Mean dia, that is 360 OD and 130 ID, mean dia is 24.5 centimeter. The mean circumference is 76.93. Distance to be fed is half of that, that is 33.45 centimeter. distance to be fed in terms of thickness of the flange is 33.45 divided by 7.2. 7.2 is the modulus of the inscribed circle, taking into consideration the heating effect of the fillet. This is 4.6 times. This is good enough. This fitting distance, this is good enough.
Hello, sir.
Chandra, you have any
Yes.
question?
Yes, sir. Sir, actually, we have a doubt regarding the neck calculation, sir. Is it an
Yes.
optimum? Is an optimum calculation for all the type of sleeves, sir? Insulating, exothermic, sand risers.
Yes, yes. It is for sand neck. The neck should be in sand.
I mean, we are asking the calculation methodology, sir.
Yeah. It is optimum. It depends upon the distance. As the distance increases, that MC has to increase. When it reaches about more than 2 times the MC, then it will be 1.1 times. But if it is 1.1 times the casting modulus, we cannot negate it. So we keep it as close as possible and keep it as 0.5 to 0.7 MC. That we have to determine depending upon the distance. Sometimes when the entire casting is in the drag, you can keep it very close. When it is in the parting line, you cannot keep it so close.
Yes,
Then
sir.
you have to lengthen it and you have to increase the neck modulus.
Yes, sir. Thank you, sir.
Okay.
There are no further questions. I think we can move ahead with the vote of thanks. So, gentlemen, we've had a very interesting technical webinar today on the topic riser design for ductile iron castings. We are sure the contents of the talk had a lot of takeaway for our audience. We would like to thank our speaker for the day, Mr. SP Arunachalam, Director Technical, Shri Venkatachalapathy Alloys Pvt Ltd, for taking time of his busy schedule and making us rich with knowledge. Further, we would like to thank all the members who joined us for this talk. I'm sure you all had a wonderful learning experience, and thank you for joining us on time and being such a wonderful audience. We from the Chennai chapter will be conducting many such interesting programs, both physical and virtual. We'll be sharing information with you soon. Looking forward to seeing you all in all our upcoming programs. Thanks so much, gentlemen. Thank you for joining us.
Thanks.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Thank you, sir.
Log out.